All right, let's talk about a technology that's, well, it's quietly reshaping just about everything. It's called metal additive manufacturing. And no, we're not talking about those little plastic trinkets you might see from a desktop 3D printer. This is a whole different ballgame. We're talking about a genuine revolution in how we build real, functional things, from critical jet engine parts to custom medical implants.
So, let me ask you a question. How do you build something that's, well, impossible? You see, for centuries, making complex stuff out of metal was all about brute force. You'd start with a big, solid block of metal and just carve away everything you didn't need. Kind of like a sculptor with a block of marble. But what happens when the design you need is hollow on the inside, or has this crazy, intricate lattice structure to make it super strong but also incredibly light? That's the exact point where the old way is just hit a wall, a hard wall. And that's where a totally new way of thinking had to take over.
And that challenge? It brings us right to this core problem that engineers have been wrestling with for decades. We can call it the manufacturing conundrum. It's this constant, frustrating tug-of-war between making something custom, how much it costs, and how complex you can actually make it.
Okay, so look at the two approaches here. On one side, you've got your traditional, or what we call subtractive manufacturing. Think about it. You're subtracting material. The big problem? It requires all this super expensive custom tooling. So if you only need one or two of something unique, the cost is just astronomical. But then, on the other side, you have metal additive manufacturing, and it completely flips the script. It's additive. It builds parts from scratch, layer by tiny microscopic layer, all from a digital blueprint. No expensive tooling needed, which means it's suddenly cost-effective to make just one custom part.
And, this quote here really just nails it. It says, this technique has drastically reduced the manufacturing constraints. And what that really means is that it's not just a small step forward. This is a giant leap. All those designs that engineers used to sketch out and then get told, sorry, can't be made, well, now they can. It's unlocking this whole new world of design and efficiency.
So how did we even get to this point? I mean, a technology this revolutionary doesn't just pop up overnight, right? It's got a really fascinating history, and it's a story of how it went from being this niche tool for making simple models to a full-blown industrial powerhouse.
Okay, let's walk through the timeline. It all kind of started back in the 80s, but with plastics, in what they called rapid prototyping. The real game changer for metal, though, came in 1994. A German company, EOS, showed off the very first prototype of what we now call direct metal laser sintering, or DMLS. Then a few years later in '98, you had Sandia National Labs developing another process called LENS. And fast forward to 2016, and boom, you've got giants like HP jumping into the market. That's when you knew this wasn't just a niche thing anymore. It was going mainstream.
So that's the backstory. But how does this stuff actually work? I mean, what's happening inside the machine? Well, there are a bunch of different names and specific techniques out there, but you can boil almost all of them down to two main methods, and they both have two things in common: superfine metal powder and a whole lot of energy. Okay, on the left, you've got powder bed fusion, or PBF. I want you to picture a big, flat bed of metal powder that's as fine as dust. Then, a super powerful laser or an electron beam comes in and zaps a specific pattern, melting and fusing the powder in that spot. You do that layer after layer, and you get incredibly complex, super accurate parts. Now, on the right is direct energy deposition, or DED. This is a bit different. Imagine a nozzle that's spraying that metal powder, or feeding a metal wire, right into an energy beam. It melts on contact and gets deposited onto a surface. It's almost like a really precise robotic welder. It's awesome for fixing expensive parts or even adding new bits onto things that are already built.
So let's zoom in on that powder bed process for a second. Here's how it goes down. First, a little roller sweeps across and lays down a perfectly even, paper-thin layer of metal powder. Then, a laser zaps down and traces the shape of that one slice of the final part, melting the powder solid. After that, the whole platform drops down just a tiny bit, the roller comes back with a fresh layer of powder, and the laser does its thing again. You just repeat that over and over and over, sometimes thousands of times, until you have a complete, solid metal part sitting in that bed of powder.
And just to be super clear, if you want the official, technical definition, this is what the standards organization ASTM says. The two key things to notice here are layer by layer and as opposed to subtractive manufacturing. I mean, that's it. That's the whole revolutionary idea right there in one sentence.
Okay, so this all sounds amazing, right? But let's get real for a minute. In the actual world of manufacturing, there's no magic bullet. No single process is perfect for every single job. It always comes down to a balancing act, a classic engineering trade-off.
And that trade-off is often called the time-cost-quality triangle. You've probably heard of this. You can pick any two. Want it fast and high quality? Yeah, that's going to cost you. Want it cheap and fast? Well, the quality is probably going to take a hit. Understanding this triangle is absolutely key to figuring out why we have these different metal 3D printing methods in the first place.
So, let's apply that triangle to the two big processes we just talked about. Take a look at DMLS, the powder bed one. It gives you this beautiful, smooth surface finish, right? High quality. But the catch is, it's pretty slow and it works best for smaller parts. And it tends to be the less expensive option. On the other hand, you've got DED. That process is way faster and you can build or fix gigantic things with it. But the trade-off? The surface is going to be rougher and the overall cost is higher. See, it's all about picking the right tool for what you need to do.
And when we talk about quality, the level of precision we can get is just mind-blowing. The data shows that some of these DMLS techniques can get the dimensional error down to less than 1/10 of a millimeter. That's thinner than a human hair, over a pretty decent-sized part, too. It's that insane level of accuracy that makes it possible to use this stuff for things where failure is not an option, like in aerospace and medicine.
So here's the really crucial thing to understand. This isn't science fiction anymore. This isn't some niche experiment happening in a lab somewhere. Metal additive manufacturing is here, right now, and it is actively changing the game for huge global industries.
And I mean, the list of industries being totally transformed just keeps growing. Just look at aerospace. General Electric prints fuel nozzles for their jet engines now. The old way, they had to weld together 20 different little pieces. The new 3D printed one, it's a single solid part. And get this, it's 25% lighter and 5 times more durable. That's a massive difference. And you're seeing that exact same kind of leap forward in medicine with custom implants made just for one patient, in the energy industry with crazy complex turbine blades, and heck, even in jewelry with designs that were just physically impossible to make before.
So, when you boil it all down, what's the big deal? Why does all this matter so much? It's because metal 3D printing lets us make things that are just fundamentally better. We're talking about parts that are lighter, which saves fuel, parts that are stronger, which makes things safer, and parts that are way more complex, which boosts performance through the roof. It's a true leap forward in what's possible with engineering.
And that leaves us with one last really big thought. For pretty much all of human history, what we could build was limited by our tools. But for the first time, that's changing. Now, our limits are less about our physical tools and more about our own imagination. So if we can build just about anything we can dream up, the real question is, what are we going to make next?